The Scribe is a very useful tool, but you can't sensibly put it in your pocket. Luckily, we have a solution. There are three seemingly impossible things about this device. For example, when we extend it in this direction, the Scribe tip extends in the opposite direction. That's counterintuitive. There are only a few mechanisms that behave like that, but one example is Henry Segerman's expanding rack. When we pull on one side of the mechanism, it expands in the other direction, in a similar way to the Scribe. But in the case of the Scribe, there's a big difference in displacement between the bronze helix and the Scribe tip. If you take a nut and a thread, when the screw is rotated, the nut moves in a linear direction. In this case, the thread is rotated clockwise, looking from the clamped end, and the nut moves from right to left. This is what the vast majority of threads do. There are actually a few places where threads behave in the exact opposite way. For example, a left-hand bicycle pedal, so it's less likely to come loose when pedaling forwards. This nut on a woodworking plane moves the blade in and out to change how thick the shaving is. In this mechanism, the nut engages with a component called a yoke, which flips the direction of movement. To compensate for this change in direction, this nut is also reverse threaded, like the left-hand bicycle pedal, so that the woodworker can rotate the nut in an intuitive, clockwise direction to increase the thickness of the wood shaving. So, if we go back to our threaded bar, but reverse the direction of one side, and fit it with a left-handed nut, you can see the nuts move in opposite directions as the screw is rotated. Both sides of this screw are threaded in the same direction, but when I rotate it, the separation of the two nuts changes. This is because the pitch of each side of the screw is different, so when the screw is rotated, one nut moves faster than the other. This is called a differential thread. If we combine these two concepts, we get a mechanism that can move two nuts in opposite directions at different speeds. I'm not sure if this mechanism has an official name, but we're going to call it the opposing differential thread. This is the principle behind our impossible Scribe idea, except the coarse right-handed thread is actually formed by two interlocking helices. Of course, in our 3D printed models, the screw itself doesn't change length, so there's still the mystery of how to make the whole mechanism shrink, but I'll get onto that in a bit. To make these interlocking helices on a manual machine, we have a few challenges to overcome. Now, I'm trying to improve my explanations so more people can understand my ramblings, so just give me a second to explain how this works from first principles. The workpiece is first mounted in a collet chuck, which is connected to the machine spindle. When the spindle rotates, the workpiece rotates. The machine spindle is then connected to the lead screw through an array of gears, and we can adjust these how we like. This lever flips the direction of the lead screw without changing the gear ratio. These two levers give me even more gear ratio options, but most importantly, this lever allows me to connect the lathe carriage to the lead screw. Off camera, I built this device, which allows me to spin a milling cutter in situ on the lathe, where my tool post normally goes. So now we can traverse the trajectory of the helix, and we can cut metal along that trajectory. Well, that's all we need to make our helix. Hazel and I thought it would be extra neat if the helices could interlock without any gaps at the ends, so we opted to make the ends of each helix square. I didn't have a clever way to machine this, so I just did it by eye, which was a bit more difficult than I anticipated, but I think I managed okay in the end. There's an extra challenge with this helix, because it must be hollow to interlock with the other one. My original plan was to first drill the hole before machining the helix, then glue in a support shaft, and then dissolve the glue to remove the shaft. Laziness got the better of me though, and I decided to try removing the core after making the helix, which turned out to be quite difficult because the helix made the drill bits wander. There was definitely a visible level of eccentricity between the helix and the hole down the middle, which we would all like to believe will teach me not to be lazy again in the future. I made the other helix from bronze, but otherwise in the same way. It also needs a hole up the middle, but this one doesn't need to break through into the helix, so that makes it nice and easy. As I mentioned earlier, these two interlocking helices form the right-handed coarse thread of our opposing differential thread mechanism, but the bronze piece needs to be rotationally coupled to the left-handed thread, which we haven't made yet by the way. And it needs to be done in such a way as to allow linear motion between the two threads. This is so that, well, firstly, the threads don't jam against each other, but it's also to allow the entire mechanism to shrink in length, as we demonstrated at the start of the video. One way to do this is to make the bronze piece hollow, but with, say, a square hole, and have that engage with a square shaft. This would allow the two pieces to slide linearly relative to each other, but lock their rotations. If you've been following the Watch project, you will know that I have a particular hatred for making square holes, and making a blind square hole deep enough is difficult. So Hazel and I came up with a different approach, and it relies on the fact you only need one flat face shared between the two parts. I first turned a brass tube and then milled away a portion in the middle. This wasn't without its challenges though, the main one being the residual stresses in the rod. Because the rod is drawn in manufacturing, which involves significant plastic deformation, you can get quite a complex residual stress distribution within the material. This basically means it wants to deform into a different shape to the one it was forced into during manufacturing. But it doesn't, because those internal stresses balance each other out. So that means if you were to remove material in an asymmetrical way, the remaining shape has to deform to balance those internal stresses again. Here you can see this component has gone banana-shaped, which is a result of longitudinal stress. In fact, from the way this shape is deformed, we can infer that the longitudinal stress towards the outside diameter of the rod was tensile relative to the centre of the rod. Now, here's the clever bit. I then glued in the halved tube into the bronze helix, but because I left the ends of the halved tube intact, it was fully constrained. Then all I had to do was use a boring tool to remove the intact end of the halved tube to reveal the asymmetrical hole all the way up the length of the bronze helix. I made the corresponding part to fit in the long hole and pinned it to the Scribe component. We opted to make the left-handed thread a 1mm pitch and glued it to the scribe. This means it moves 1/8 the distance of the bronze helix when it's unscrewed. Earlier I said there are 3 seemingly impossible things about this device. The first thing is that the scribe tip moves in the opposite direction to the bronze helix, which we've covered with differential threads. The second impossible thing is what stops the bronze helix from falling off the end. As you've seen, there's no hidden pin or anything like that inside the helices stopping it from coming apart. So how does that work? The best way to explain this is to jump back to Hazel's 3D printed model of the opposing differential thread. Imagine for a second the coarse right-handed thread with the red nut represents the interlocking helix assembly, and the fine left-handed thread represents the hidden thread we just made. Now, if I offset the left-handed nut and rotate the screw until the left-handed nut runs out of thread, the mechanism stops moving. You can see that the red nut, i.e. the bronze helix, has plenty of room to move, but it can't because of the other thread. This is how we keep the helix trapped. And this brings us on to the third and final impossible feature. How is the mechanism assembled? If the scribe is in place, you can't interlock the helices, and if the helices are assembled, where does the scribe fit? The secret is that the steel helix, which forms the bottom part of the scribe, actually comes apart into 2 pieces. Let's finish up the last part and see how it all goes together. This project was a gift for Francis from Project Havoc as part of the 2026 Toolroom Takeover collaboration. If you haven't already, make sure you check out his excellent channel and see what he thought to the impossible scribe. By the way, if you want to machine this for yourself, you can download drawings and CAD from our Patreon page. Hazel's also tweaked and scaled the design to work as a big novelty pen that can be 3D printed. You can download these files for free from Patreon. So what did we get? Well, imagine you have to fit some hardware like a hinge, and you want to transfer the hole position from the component to the contacting surface. Have you noticed how difficult it is to mark the center of that hole? Sure, you can draw a circle and then try center punching the middle of the circle, but your center punch never ends up in the middle. Marius Hornberger made us this absolutely stunning kit to do just that, and look at the little helices. To use it, first choose the appropriately sized chuck and unscrew the 2 halves. The drill bit is clamped in place with a tiny ER collet. These brass guides locate with the hole in the hardware, forcing the drill bit to perfectly transfer the position of that hole. Hazel and I absolutely love it, and we can't wait to put it to good use. Thanks, Marius. Make sure you check out his video on how he made this, and while you're doing, have a look at the rest of the collaboration playlist. Thanks for watching. I'll see you in the next video.